Welcome to my channel, Random Realm. I found this video the other day and really wanted to share it with you. The following video description that I'm going to read to you next explains the background to this video. So, these are not my words. Here goes. My dad was always proud of having worked on the electric car project, named ETV1, at Chrysler in the late 1970s and early 1980s. This project was a joint project with the US Department of Energy, General Electric, and other companies. I found this video of the ETV1 car at his house after he passed away and wanted to share it with anyone who may be interested. Well, I for one was immensely interested. But anyway, I'll stop talking and let you sit back, relax, and enjoy this video.
This is ETV1, the first electric test vehicle developed for the U.S. Department of Energy's near-term electric vehicle program. It is the result of 2 years of hard work, 2 years of bringing together the best ideas of a dedicated team of scientists and engineers.
Well, in your simulations, George, you were assuming we could put essentially unlimited current, like 300 amps or thereabouts, into the battery. Is that right?
That is correct.
These technical people were presented with a challenge to design an advanced electric vehicle that would be suitable for mass production in the mid-1980s. A car like ETV1 doesn't just happen. Like the vehicles from the space program, it was designed systematically from the ground up to meet specific goals. Acceleration from 0 to 30 miles per hour in just 9 seconds. Ability to maintain 50 miles per hour up a mile-long 5% grade. Passing speed of 60 miles per hour. And the target range for stop-and-go urban driving was 75 miles between battery charges with a full payload of 4 passengers. Another factor was purchase price. If produced in quantities of 100,000 or more per year, it should be available for the price equivalent of $5,000 in 1975 dollars, or about $6,400 in 1979. Its life cycle cost should not exceed 15 cents per mile based on 100,000 miles in 10 years. Based on these objectives, and more, the ultimate design of the car evolved. The result is a 4-passenger, front-wheel drive subcompact, powered by a 20-horsepower electric motor. It represents a new high mark in electric vehicle technology.
For that, I think we could put it on extender cables and operate it outside of the vehicle, but...
As prime contractors performing under the technical management of the Jet Propulsion Laboratory in Pasadena, California, scientists and engineers at the General Electric Research and Development Center in Schenectady, New York, tackled the challenge of designing a technically advanced and reliable drive system for ETV1. Of special importance was ensuring electrical safety during operation and maintenance. Their major goal was to devise the most efficient method for controlling the electric motor. For the more efficiently the motor could be controlled, the farther the car could go between recharges. Based on extensive computer simulation, the engineers decided to regulate the motor through separate electrical control circuits for the armature, the rotating core, and field, the outer windings. They also chose to equip the car with regenerative braking. When the brakes are applied, the motor becomes a generator that helps to recharge the batteries, squeezing out more miles between charge-ups.
It looks like we can get a very significant range improvement with regenerative braking, but we're concerned about a problem about how much energy we can really put back into the battery during a short time period.
As basic decisions about the drive system were made, engineers began assembling experimental circuits for the central electronic assembly, called the Power Conditioning Unit, that controls all the electricity running through the vehicle. The researchers decided on a package of 18 6-volt batteries to provide the electrical energy to move the car. With 400 amps of current available, the peak power is equivalent to 1,000 40-watt bulbs operating simultaneously. The key to controlling all this power is a low-cost, high-power solid-state electronic device called a Darlington transistor. This device can turn all the current from the batteries on or off in a millionth of a second. The heart of the Darlington transistor is a silicon chip half the size of a postage stamp. The chip is mounted in a special copper cooling package, 2 of which are put together in a power module 1/10 the cost and half the size of previous devices with the same capability. Later, 4 of these power modules will become part of the power conditioning unit. Power transistors based on this technology will be commercially available in the future. Meanwhile, in Pittsfield, Massachusetts, experts in the construction of rugged electronic systems prepared to build the final power conditioning unit for ETV-1. Based on working models constructed in Schenectady, computers traced out designs for the unit's printed circuit boards. In Schenectady, engineers began work on the car's full-time brain, a microcomputer. It provides overall electrical control for the vehicle by directing the switching of the power conditioning unit for forward and reverse, acceleration, regenerative braking, and battery charging. Next, the power conditioning unit was tested. Connected to a bank of batteries, like those in the car, it operated an electric motor bolted to a heavy flywheel. Under manual control, without the microcomputer, the power conditioning unit showed that it could start and stop a 3,800-pound car efficiently. As this milestone was reached, assembly of the final power control units, incorporating the microcomputer, was begun. Once completed, these units were tested under load to prove conclusively that they would work in the completed electric vehicle.
These are the key issues that seem to be pointing towards going with this rotated cell design and changing the plates 90 degrees. Is there anything
At the
else?
same time, in Milwaukee, scientists and engineers at Globe Union Incorporated were designing batteries for ETV-1. Their challenge was to find new ways to store more electrical energy in the batteries without adding more weight. The completed car already would be heavy in comparison with conventional cars of the same size. The team met the challenge, and a battery with 25% more storage capacity per pound emerged from their drawing boards and design computers. Tests on prototype batteries confirmed this increase in storage capacity, which the researchers achieved by a number of innovations, including turning the plates 90 degrees from their location in conventional cells. The new batteries have an anticipated life of 500 charge-discharge cycles, and maintenance is simplified. Water levels in all the batteries can be topped up through a common filler tube. In the completed electric vehicle, the batteries, electrically isolated from the chassis, are contained in a T-shaped metal tray. This tray can be unbolted and lowered from the car to gain access to the batteries. This design was chosen as the best solution, offering lightweight, crashworthiness, and minimal impact on passenger seating comfort.
I've shown the spare tire there. But you see where that spare tire goes well forward of the battery pack? How do you feel about that with a 5-mile-an-hour barrier folding? What's the dimension that the front of the car crushes?
For a 30-mile-an-hour impact, approximately 30 inches.
At the outset, Chrysler Corporation's research office was selected to play a major role in the design of the vehicle. Working with the prime contractor, Chrysler was responsible for vehicle engineering, fabrication and assembly, production costing, and vehicle testing. From the beginning, ETV-1 was designed to meet federal motor vehicle safety standards. Computer programs were used to predict and simulate crashworthiness. The designers also realized the body must be as light as possible, incorporating extensive use of light alloys, and have excellent aerodynamic characteristics. Air drag and excess weight can ruin the performance of an electric car. When a satisfactory basic body style had been identified, 3/8 scale models were tested in a wind tunnel, and the design was modified to reduce its wind resistance under normal driving conditions. At last, the car took its final shape. At the same time, engineers were asking the question, can we build an electric subcompact that will ride and handle well even though it weighs 50% more than the same-sized conventional car? To find the answer, the engineers constructed a mule car. Based on the chassis of a conventional subcompact, this gasoline-powered automobile was ballasted to duplicate the weight of ETV-1. A battery tray that simulated the battery compartment of the final electric vehicle was bolted into place. The suspension was redesigned with new geometry and stiffer springs to control a car that would weigh 3,920 pounds when loaded with 4 passengers. The mule car was put through its paces on a test track to check its handling in panic avoidance situations as well as in ordinary traffic. The response and predictability of the mule car assured the engineers that the completed ETV-1 would handle as well as a conventional automobile. After track testing of the mule car's ride, handling, and braking, it was modified to duplicate exactly the structural properties of the electric vehicle. Then, it was crashed. Engineers ran the mule car into a concrete barrier at 30 miles per hour. The results verified that the electric vehicle would meet federal motor vehicle safety standards for frontal impact. The body for ETV-1 was fabricated at Modern Engineering Services Incorporated in Detroit. Body forms were built up in wood. Next, cast in plaster. And then molded in sand to create the forms for stamping the sheet metal. On a gridded assembly platform, body pieces were carefully positioned and welded into place. Sheets of Lexan plastic were thermoformed to create the side and rear windows. Finally, the electric vehicle was completed. At the proving grounds, the testing program began. To the driver, the controls of the electric vehicle look, feel, and operate like those of a conventional automobile. The microcomputer, located behind the instrument panel, receives inputs from a variety of locations throughout the car. Including the brake and accelerator pedals, the drive, neutral, and reverse control, a safety interlock in the driver's seat, and the batteries. But when the driver punches drive and steps on the accelerator, he is aware only of the motion of the car and the humming of the power conditioning unit. The track tests confirmed that the car had met its basic design goals: 0 to 30 miles per hour in 9 seconds, Top speed 65 miles per hour. It can climb a mile-long 5% grade at a constant 50 miles per hour. Handling is good, and the feel is crisp and positive. During the Society of Automotive Engineers Urban Driving Cycle, a standard test for stop-and-go driving, ETV1 will cover about 70 miles before it needs to be recharged. Back at the garage, the car was connected to a battery charger for overnight recharge, as it would be at home. And engineers checked the motor, drive system, and the safety interlock that disconnects the electrical system when the hood is raised. Continued tests at the proving grounds revealed that a typical driver and one passenger can obtain a range of 100 miles at a constant 45 miles per hour. They have also found that ETV1 is quiet, comfortable, and pleasant.
What we have to recognize here is a compromise between the style appearance of the vehicle and the need for a low slip factor for aerodynamic purposes.
Do we have to remove that from the vehicle to test it, or can we?
The quest to develop a practical electric car is one of the most challenging problems facing the nation's scientists and engineers. The Department of Energy's near-term electric vehicle program has spurred the search for a solution, and ETV1, equipped with tomorrow's technology, has passed an important milestone on the road to this goal. The program is one of many steps being taken by the Department of Energy to stimulate the ultimate large-scale commercialization of electric vehicles and thereby reduce U.S. dependence on petroleum.
Thanks very much for watching. Please like and subscribe for more interesting videos just like this one.